Hello humans, we are going to have a quick tour of some of the materials, elements, and compounds that we have in the classroom. You've probably seen these during labs, and we're going to take some guided notes with these things. So we started out before we got into the periodic table of elements, and we were learning about mixtures and solutions and things like that. And one of the last things we learned about were alloys, which are mixtures of metals. Okay, so here's an example of an alloy of lead and tin, and this is not a compound; it's a mixture. So we can separate these two things without using a chemical reaction. We're not doing that in this video. What we're going to do today is try to recognize what our metals and our nonmetals do with each other to bond and make new materials. All right, so let's try to get as close as we can. We've got a little lump of zinc here. It is a metal. It's shiny. It would conduct electricity if we had a circuit for it. We could pound this into a flat piece because it's malleable. Here's a piece of copper, which is what old pennies were made of. A lot of the wiring in our houses at school are made of copper. It's malleable. We could bend this. We could pound it flat. We could make a copper foil out of it like you might use aluminum foil at home. Here is tin, which some people still call aluminum foil tin foil. It's not made out of tin. Tin is metallic. You can see that it's shiny. It's easy to melt. We could melt this in the classroom with a Bunsen burner if we wanted to. But all of these are to the left of the stair step. So copper, zinc, tin. Our next example of here is aluminum. It's getting closer to the stair step. Once again, it's shiny. It's malleable. This flat spot was put on there by pounding. You can make wires out of aluminum, but aluminum tends to be a little more brittle than copper and these others because it's getting closer to the stair steps. It's less metallic than these are. It has a lower ability to conduct electricity and heat, and it's less malleable. That means if we strike this with a hammer, it's more likely to crack than it is to just flatten out. So as we move across the periodic table, we only have one example of a metalloid in the classroom. It's silicon. These others are in the classroom, but they're in compounds. So the one example we have is silicon. And silicon, let's see if we can get a focus on this. Silicon is a true metalloid. It looks metallic. It's got some shiny bits to it. But on the other hand, it has a property of a nonmetal, and that is if we were to smack it, it pulverizes. It turns into a powder instead of being malleable like the metals. Like I said, if we pound it on the zinc, it would just flatten out. If we pound on the silicon, because it is a metalloid, it is going to be shiny like a metal, somewhat conductive, but it's going to powder because it's not malleable or ductile. Just as an example, one compound that silicon will form, and this is a very interesting thing to me. We've got a material that looks like a shiny metal rock. When you combine it with oxygen, you have silicon dioxide, which is glass. Okay, and of course the oxygen would come from the atmosphere. All right, right up from silicon, we have our first nonmetal. Let's shift our periodic tables. Our first nonmetal that we're going to look at is carbon. Carbon is a black material. If we took this and hit it with a hammer, it would pulverize. It would turn into a powder. You can see some residue there. Carbon, because it is in group 14 or IV, has 4 valence electrons, and carbon is the center of the study of organic chemistry. People invest their whole lives studying molecules made with carbon. Okay, our next nonmetal is sulfur. Sulfur is distinguishable by its color. You can tell that this has been pounded a little bit. It is obviously not metallic. It's not shiny. If we hit this or squeeze it with a pair of pliers, it crumbles. Okay, it is not malleable. This is rather easy to melt in class. We've done that in lab. What else do I need to say about sulfur? Sulfur is one of those things that in our classroom, we use sulfur. And looking through the camera here, we use copper excuse me, and we all use oxygen. And if we take all three of those things and let them do what they do, we can't make chemical reactions happen. We can just watch them. But copper, sulfur, and oxygen from the atmosphere becomes copper sulfate. And we've been using this in our solutions lab, and we've dissolved this in water. It's soluble. The copper's not soluble. Oxygen is somewhat soluble in water. Sulfur is not soluble, but when we form a compound, we have new characteristics. This material is, well, you can see that the light gets transmitted through it. It is obviously a different color than anything we started with. It is still, it still crushes like a nonmetal. It's not conductive of electricity. Well, I think it is if you dissolve it in water. And then you also should notice that it has a very particular shape. Every crystal that we allow to come out of solution has a very similar geometry. And I don't think you can see very well on this one, but each of these little pieces has the same external shape as these bigger pieces. And if we would allow these crystals to form slowly, they would continue on with this shape because of the crystal lattice of the bonds here. So we've got a metal and an SO4 ion combined. This would be a covalent bond. That's another video. Another example of compounds where if we took a little piece of the zinc metal and had it react with oxygen, it makes zinc oxide. Once again, the oxygen is a clear gas from the atmosphere. The zinc is a metallic element that we could pound flat, but when it reacts, it turns into this very white powder. This is if you were to see this in person, it is whiter than a sheet of paper. It's a very useful compound for protecting against sunburn and diaper rash. Anyway, we use this in class. It's not water soluble. It's not conductive. And that's because we have a new compound that forms from the zinc and the oxygen in the air. And then, let's see, we've got one more here. And I think we're actually going to be able to demonstrate this one forming in front of us. So magnesium, and I've left the periodic table on the other end of the table here. But magnesium is a metal. I've still got some zinc oxide on my finger, sorry. But it's a metal. It's malleable. We could take this with a pair of pliers and squeeze it into new shapes. We could pound it into new shapes. It is conductive. It's not as brittle as the aluminum. So we could wrap this up. We could make wires out of it. It's easily melted and mixed with other metals. But there's something else that's handy-dandy to do in class with this. So we're learning about the fact that oxygen and hydrogen and nitrogen and fluorine, chlorine and iodine and bromine are all diatomic molecules. So oxygen is floating around in our classroom, and they are paired up. They're bonded with each other, so the oxygens are bound up. Well, in our example, we've got a piece of magnesium here, which is a bunch of atoms of magnesium metal, and they share their outermost electrons, their valence electrons, in a metallic bond, which is what makes them conductive. So if you put more electrons in on one side, they would just go out the other side. But in this case, if we want to change the characteristics of the magnesium by combining it with oxygen, all we have to do is increase the rate of the oxygen hitting the magnesium. So what we've got here is a little piece of magnesium, and we've kind of shredded the end up. We're going to add a little bit of heat. And you'll notice that it's reacting with the oxygen in the air. It's releasing a lot of energy. And then as it finishes up, so it started out as this very flexible, malleable metal that you could actually probably make a little bit of a spring out of. But now that the reaction has happened, now we have an oxide of this metal. And so it's no longer metallic, and it's no longer a clear gas. It's got characteristics of change altogether. All right, let's make another video about diatomic molecules and bonding, and let's complete our guided notes.